All right. So if the amount is 0, actually we have a solution, right? If the amount is less than 0, or the number of denomination is 0, we don't have any solutions, right? So we return an empty tuple. A tuple with no elements is no solutions, right? And then what are we going to do? We're going to return the count change exactly as before, right? So what happens here is that, you see, here we have decided to use denominations of 0. Yeah? So the accumulated solution actually grows by the denomination that we have just added. Yes? Whereas here, we haven't used the coin. So the accumulated solution stays the same. Okay? So let's make this more readable. Okay, now how do we call this procedure? You see, we have an extra argument. Whenever I'm going to call it, so I'm going to go back and get all these 3 examples. Get all these 3 examples. Right? And then this count change needs to have an extra argument here. Oh, and last time I gave you lists instead of tuples. And you notice that they're quite interchangeable because of that, because we didn't even notice that they were lists instead of tuples. All right, so there needs to be an extra argument. What is that argument? Well, initially the accumulated solution is empty, right? So we just put the empty accumulated solution. All right, if we run this, all right, let's go to the easy ones, right? So the number of ways to return change for 15 cents, yeah? With denominations, these is, and this is the first way, a 10 and a 5, and this is the second way, right? And we remember from last time that there are only 2 ways. The number of ways of returning change for 20, we have 3 ways, right? We have 4 ways, sorry. I can just give back a 20. It's a valid coin, it's a valid way of returning change. I can do 2 10s. I can do a 10 and 2 5s, or I can do 4 5s, right? For $1, well, you can check them on your own, right? Obviously, there are many of them. You can be pretty sure it's all of them. Notice that the last one, we're expecting the last one to have 20 5s. Yeah. One thing is randomly to check that all of them add up to 100, right? So Like this one, it's pretty clear that adds up to 100, right? So yeah, randomly, the ones that are a bit shorter, we can check that this is the case. This one is all tens, so there should be 10 tens, right? 2, 4, 6, 8, 10, yeah. So again, we can, from this one, we can actually print them all if we want, right? But notice how once we have tuples, we can do actually a lot more, right? We can collect and get the solution. Previously, all we could do is count those, so that's those solutions. Now, there's another thing that I want to introduce here, right? So notice that once we have finished writing this procedure, right? Once we have finished writing this procedure, what happens? We give it to the world, and people will use it, right? This is how they use it. This is one use, this is another use, right? We put in a package, people open up Python, they say import count change, and then they invoke it, right? So the use by other people is invocations. Most of the time they don't look at this code, right? Sorry, I selected too much. But it's very important for them to look at this and understand this needs to make sense. Now, from somebody who hasn't seen the code, the need to pass in the same constant argument, the empty argument there, seems like a drag, seems like an inconvenience, right? Doesn't make sense. Why should we force the user to always pass the very same argument, right? So we would like to hide this from the user. We like to hide this part from the user. So we introduce the concept of a helper, right? So we call this helper, and then these invocations become helper and helper. And then we can hide the helper inside another procedure. I'm going to go here, indent this by 4 spaces. And then I say def count change amount and denominations. And then here, once I'm done with the helper, I'm going to say return and helper amount denominations okay, this guy is helping me, and then empty, right? So instead of asking the external user to pass in empty, I pass it here for them, right? I use the helper and force this argument to always be empty, right? So that this is hidden. Now I can go here and remove this extra argument. This is no longer necessary. All right. This entire procedure is hidden inside count change, which means that here, at this point, if I try to say helper, helper will not be recognized. Doesn't exist. It only exists inside that procedure. So I missed bracket, and then these should also be brackets. So it's less important because this is inside a string, but for conformity, let's do that. All right, and we get exactly the same result, right? Just that the use is more elegant, all right? Why is this necessary? Well, this is the one way of passing down whatever has previously been computed, right? So we are accumulating a partial result, right? Whenever we have used a 50 or whatever we use, we record it inside this argument so that at the point of finding a solution, we can return that solution fully, right? So as we go down bit by bit, yeah, the partial solution grows into a full solution. Cool. We're going to play with more numeric tuples next time. So we're going to look at prime numbers and different ways of computing Fibonacci. And then we're going to look at other types of collections, lists, sets, dictionaries. What will happen after that is we're going to talk a bit about graphics. Actually, maybe next week, I will also introduce the graphics. We're going to talk a little bit about fractals. And then we're going to go and do a game. We're going to do a very simple version of a game called Asteroids. It's an arcade game from like 30, 40 years ago. You're going to see that it can be done in 3 hours, in the span of 3 hours. That is also going to be part of your homework, right? So assignment 4 is going to be part of your, is going to rely on this. And because I never get the same game, in each new installment of the course, I haven't set assignment 4 yet, right? So I'm going to set up assignment 4 when we have finished the game and the code is available, right? It's going to be based on whatever we produce in class. This will also make sure that you don't cheat. You can't take the solution from last year or last semester, yeah? So this will be the one assignment where you really have to solve it on your own. Cool. And in the last week, we're going to do data analysis. We're going to learn a little bit about data crunching, which is stuff that you already do in a course on R. Is that the R course still available? Yeah, right. So you're going to learn how to do some of that stuff in Python. It's going to be very little. Questions? If not, cool. Class dismissed. See you next time. Next time, I won't be here. So it's going to be fully remote. If you don't want to come to class, don't. If you want to come here, of course, feel free to. The Zoom link is there. Just use it, right? There's going to be a video recording as well. Okay, so I'm going to stop everything.
You're only not here for next week, right? Or are you not coming anymore?
No. Well, I'll see. If I'm in Singapore, I will.
Okay, so just next week that you can't.
And if I don't get sick while traveling, yeah, I'll try to be. I'll definitely be here in the last class.
Okay, but so like next week,
if you are. But so if you want, why are you asking? Because you want a consultation or?
Yeah, maybe. So
yeah. We can arrange again one that is remote and.
Okay. Remote meetings.
Okay.
And then is it possible for you to just send us your code after the lesson?
It's uploaded. It's on your canvas.
Oh, I see.
Oh, it's here, right? So if I go, I'm not sure if I'm still. I go to files.
Mm-hmm.
Yeah. Week 1 is here. Have I? Yeah. So I'm going to upload right now. Let me do that right now.
Okay. And then we can like go into
for this week.
Okay.
And that's where you're going to find
So this is what we did today, right? Like
yeah.
That one? Okay. I'll go and look at it again because I think I am trying. Like if I try to write it down and listen to it at the same time, like it's just too much.
Okay. So but you can always say that. You can always slow me down.
Oh. No, I mean it's fine.
You can always say, yeah. Can you go a bit slower? Or can you wait until I finish?
I'm sure everybody understands you. Like I'm just like they're like, what's going on? Okay.
Cool. So the files are up.
Okay, thank you. I'll go study it again.
For the Hanoi game yesterday, right?
Yeah.
So this was the code yesterday. So what I understand from that is that we take everything except for the biggest block, move it to the intermediary, then the biggest block goes to the end,
Mm-hmm.
and then move the everything but the biggest onto the
Mhm.
end. But like, when did the second part happen, where you move the biggest to the end block? Because like,
Here, right? The last line is exactly that.
but that's n minus 1, right? So isn't that moving everything but the biggest
Yeah.
from the middle to the end?
When do I move the biggest?
Yeah,
Yeah.
when did you move the biggest?
In the middle here. This one moves the right. This middle move is going to be exactly
Move a disc.
the largest disk between start and end.
Oh, but this is just something that will be printed out, right? So like, the move doesn't actually happen here,
Well, I can't move it because
or because it's a
it's not
an
right.
actual block.
Yeah. So I'm telling you what the moves are, so you can
Ah.
go and execute them. Right.
Okay, so in the first, like the very first one, it'll tell you to move the smallest one, like the number 1 piece to the end block. Okay,
No. So the thing is recursive, right?
Mm-hmm.
Yeah. So then I'm gonna. So when I say Hanoi
Yeah.
of n minus 1, I'm gonna go to the top, right?
Mm-hmm.
And I'm going to solve the problem. So let's say I want to solve the problem for 3, right? When I say, oh, solve the problem for 2, it goes back, and now n is 2, and different start and end and mid, right? And then it goes in and say, oh, solve it for 1, n minus 1 from 2 goes to 1, right? And it goes back to the top. And then is n 0? No.
No.
So then when you solve it for 1, right? So solve it for 0, right? When you solve it for 0, go back to the top. Yeah. So it's actually easier if we look at today's solution, right? So you start with Hanoi. I have never been lucky here for some reason. Unlike NUS. I'm bringing my own from London. So we have Hanoi, let's say of 3, and we have 1, 2, 3 here, or 1, 3, 2, yeah. So this is not 0, right?
Yeah.
So forget about a print. Let's do today's solution, right? So if you look at today's solution, because it's not 0, what I have to compute is Hanoi of 2 and 1, 2, 3 plus a move from 1 to 3 plus Hanoi. Right, so this is algebra now. 2 and 2, 3, 1. Yeah, let's put it on the where is it? Yeah, so we're here. Yeah. So if I want to compute this, I have to compute this, yeah? Right? Now, if I want to compute this, I'm going to have to start with computing this, which is what? Exactly the same definition, right? So I'm going to look at that definition over there. So Hanoi 2 and 1, 2, 3 is going to be, this is not 0, right? Hanoi 1 and what do we do here? 1, 3, 2 plus 1, 2 plus Hanoi 1 and 3 3, 2, 1, yes. Right. And this part remains the same, yeah?
Yeah.
This part remains the same, right? It's algebra. So this part goes in here.
Yeah.
So I'm going to keep going. Yeah. So Hanoi is going to result in Hanoi 0 plus, and something, I don't care what it is,
yeah.
plus 1, 3 plus Hanoi 0 and something something plus, and this entire thing goes here, yeah? Now, this is going to be the empty thing. It's going to be the empty thing, yeah? So I start with having 1, 3, and then I can move on. Then I'm going to have 1, 3 plus, sorry, comma, 1, 2 plus, and I'm going to have to compute this. And I'm going to go again to the definition. Yeah? Now, and you're going to get the solutions, yeah? Is it clear? Now what happens if I have prints?
Where?
Let's say instead of having those pluses, let's say I have the print, right? It's last time solution, right? So you can think of, instead of having plus, you can think of the computer defining a sequence of actions. First I'm going to do these things, then I'm going to do these things, then I'm going to do
But
these
it's
things,
using
right?
the same method as we can see.
Yes, exactly here, right? So you're going to say, oh, I'm going to do the actions provided by this, then I'm going to do the print of this guy, then I'm going to do the actions provided by this, right? And then it will expand it, and then it will always evaluate to the left. And as soon as you have some concrete results, if there's actions associated with this element, the actions will be executed. Yeah, and it keeps going until